Welcome to everybody. I will be explaining this first presentation a little bit more on the technology that we have developed in the latest years. So please, Maria, my colleagues, before I have already explained what is the context. So the problem that we see here in front of us is to decarbonize the industries in the next few years. So we have to understand what is the way to do that, particularly in the industrial sector. As you can see here in this slide, there is a huge amount of energy that can be decarbonized. And so far in the industrial sector, there are no available technologies for the medium-high temperature sector. So you can see here that around 50%, 55% of the industry sector is related to heat consumptions. And for that, 75% is due to fossil fuel. So there is a huge amount of energy that can be and must be decarbonized nowadays. We will see how the energy storage can play a role on that. So there are three topics that can be combined together and that can lead to the necessity to install thermal energy storage. The first one is about the need for decarbonization. 50% of heat incidence on CO2 emissions is just related to the industrial sector. Then we have to consider that CO2 costs are going to increase. Nowadays are higher than in the latest, in the recent past. But in the few next years, in 5-10 years, the forecasts are scheduled to be doubling the CO2 cost. So this is adding, let's say, problems to the economics of decarbonization. And the third point is to allow for much more introduction of renewable energy. The renewable energy, photovoltaics and wind is nowadays pretty cheap. It's maybe the cheapest way to produce electricity, but they are intermittent. So only solution that rely directly on electricity cannot provide continuous heat. That is, in most cases is requested in the industry. So all these 3 points lead to the necessity to have a storage. Thermal energy storage, particularly when charged by renewable electricity or also directly by the grid, when the grid offers very low cost prices, that is happening sometimes more and more frequently nowadays in most countries of the world, that is leading us to bring on the necessity to develop thermal energy storage. So we see the thermal energy storage as a real enabler for providing dispatchable green heat and helping to reach net zero in the next few years. So under these premises, let's see how the technology has been developed. This is, let's say, what you can see here in this slide is, let's say, what we have realized in the past is we started with our technology that is essentially based on thermal energy storage, unique technology based on fluidized bed of solid particles. We have developed this technology with a real plant already in 2016, after around 5 years of previous development. Here you can see concentrated the solar power system that has been working for around 6 years in Sicily, A2A plant, where we were able to capture the solar energy by mirrors and by reflecting with a beam down mirror, the big one you can see on top on the picture. The concentrated solar power was able to increase the temperature of the fluidized bed up to over 600 Celsius, 620. So this was our first experience demonstrating the capability of a thermal energy storage developed with the fluidized bed solutions to work perfectly and to reach higher temperature than molten salts that conventional technology could do. I will be skipping technical details, but let's focus on why solid particles. We use solid particles for storing energy. Solid particles have several advantages. First of all, we investigated different kinds of solid particles. We are using so far very common silica sand. Silica sand is the second material available in the world. So it's pretty available worldwide and is also very, very inexpensive. The properties, technical properties are very suitable to be fluidized. We have been making tests to check what are the conditions to have the system fluidized. We will be explaining a little bit later what means fluidization. Anyway, the reason why we use solid particles is that solid particles may reach much higher temperature than other material like molten salts without having any degradation. They can be taken up to more than 1000 degrees without being stable, without any decomposition. Then we can directly heat the solid particles without any other intermediate heat transfer fluid, which is an advantage. Also, they have no freezing or decomposition problems, and also they don't need other equipment to be kept solids. And finally, they also are very stable. There is no risk of a fire, like in case of, for example, electrical batteries can be happening sometimes. Here you can see in this slide how appears the fluidization. Fluidization means we have a bed. You can see in this, inside this tank, you can see here, there are around 3 meters of sand. We inject high pressure air, and the air is making this sand bubbling. By bubbling, when fluidizing, the sand assumes the behavior of a fluid. The behavior of a fluid involves very high heat transmission coefficients, and this is helping so much in taking the heat from, let's say, electricity, as well as from the sun, and to release it to the heat transfer fluid that we produce. In this case, we produce steam, high temperature steam. So the system is working in two ways. We fluidize the system, we inject the air when we want to introduce electricity and transform into heat by increasing the temperature of the sand. And then we also fluidize when we have to produce steam. When these two conditions are not requested, when the heat must just be kept inside the system is not fluidized, the sand settles down, is no more bubbling, and this is helping in reducing the heat losses in the environment. So let's come to this technology. After the experience with the concentrated solar power, we have developed this specific solution, which is no more charged by solar direct radiation, but rather with electricity, preferably green electricity from photovoltaics or from wind power, but also from the grid. Nowadays, in the Nordics of Europe, in Spain, and in California, in several countries, there are already many, many hours where electricity is costing less than gas. So this is something that has to be considered, because if we want to decarbonize, having also an eye to the competitiveness, this system is suitable because we can select what are the hours when the system can be charged, the few hours in the day where the cost is cheapest. And so we charge the electricity, the heat, with this condition. And then we can produce the heat continuously according to the demand of the specific plants. In this case, we get a decarbonization of the system and the reduction of the CO2 emissions. How it appears, the system, you can see a sketch there, but also the module here. We have, let's say, the fluidized bed, which is directly heated by resistive heaters, by Joule effect, and directly releases the heat to the heat transfer fluid producing steam. We have only one device. It's the technology with the fluid bed is unique also in this, because it's the only technologies in our knowledge that can integrate in only one device these three functions: to charge electricity in the module, to store the electricity in the same module, and to produce steam in the same module. In other words, this can be seen as an electrical boiler with integrated thermal energy storage. Here you can see what is inside. Let's see just the major equipment. You can see on the top the electrical heaters, which are hanging from the roof. They are bringing electricity and are immersed in the fluidized bed, which is able to receive the heat. The fluidized bed is heated up to temperature over 600, 620 degrees. And then when discharged, we activate the feed water pumps, which are, let's say, delivering water to the embedded exchangers, which are also immersed in the sand. Everything is fluidized by means of the fluidization air injection manifolds, which are the white color tubes that you see in the bottom. Of course, the casing, you can see here, it's just carbon steel casing with internal thermal insulation to limit the heat losses in the environment. Here, just two sketches, but I will not be boring you with too many details. We have mainly two systems. One is the fluidization system that is delivering the air to the system to fluidize, and then the hot air that is coming out of the system is going to a preheater, an air preheater, which is that piece of equipment you see on the back of the screen. The other system is the steam generation system. We use once-through heat exchangers immersed in the sand to produce superheated steam. The superheated steam is then brought down with temperature by a desuperheating system by mixing automatically a certain amount of fresh water with the superheated steam to keep the outlet steam temperature and pressure at the desired values. So far, we are targeting temperature in the medium-high temperature range. Let's say going from around 150 to 400 degrees Celsius. The system is modular, has been thought to be modular. As you can see in the small picture of the blue system, this is, let's say, the smallest size. It's just a pilot, but by aligning more of these sections in the same chamber, we can increase the heat capacity, the power input, and the power output to the requested needs. So it's modular. And this can be providing, let's say, also different kind of configuration. We can put modules in parallel configuration if we want to increase the storage capacity, but also we can install the system in serial configuration if we want to increase the temperature of the steam up to 600 Celsius, which is temperature suitable also to drive a steam turbine in case it is desired. So here we can see that basically we cover from short duration, but essentially long duration times for discharging energy and for storing energy. And we can cover also temperature of steam, generated steam from, let's say, temperature which are not suitable for heat pumps. Heat pumps are, of course, a way to decarbonize, but nowadays the heat pumps are not suitable to provide steam at a temperature over 150, 170 degrees. We can go higher and we can provide storage. So the applications can be several. Here we have just a few cases. Most of our, let's say, potential customers are asking us, for example, to integrate our system in combined heat and power. Combined heat and power is very efficient, we know, but is also strict. It's pretty rigid in the generation of electricity and steam. You can't change the heat to power ratio. It's pretty fixed. On the contrary, when we install a heat storage, like the MGTS system, we can make the system, we can decouple the electricity production from the heat production. And this makes the system more flexible. And also we can charge the system, the MGTS system, both by the power, which is generated by the CHP system, because sometimes, you know, for example, in pulp and papers or in food industries, the major request is for heat, not for electricity. So when the plant requests heat and not electricity, the plant may have extra electricity, surplus of electricity. And in that case, rather than selling to the grid at low cost, we can keep in the system, we can store in the system, and we can release it when desired in the form of steam. So this is, let's say, a way to help also other systems like CHP to be more flexible and to decarbonize also to reduce the fuel, because anyway, we can add electricity from the grid at low cost or dedicated a renewable plant to reduce the fossil fuel consumptions. Another possible service that the system is able to provide is grid services. We have been working with the Italian transmission regulator, TSO, to understand how the system can be providing grid services. And according to the Italian grid regulation code, that perhaps is one of the most stringent in this field, we can say that the system is suitable to provide secondary regulation, tertiary regulation, congestion resolution and balancing, and likely we are working also on the primary regulation. This is very important to consider because it's something that both heat pumps and also electrical boilers cannot provide. So it's something also adding, let's say, flexibility to the grid and additional value for the customers. So major fields of application of the technology. As said, let's say the technology is able to provide steam at whatever temperature from 100 to 600, let's say, to all the kind of temperature and pressure which is requested in the industry. In most cases, the first wave, let's call the first wave of application we are encountering and we are targeting so far is with this target of medium temperature, around 150 to 350, where there are a lot of industries that you can see mentioned here, for example, in the agricultural, in the petrochemical, construction, energy industries, food and tobacco, mining. Mining, for example, also alumina refining is requesting in the digestion process of alumina steam temperature at 300 degrees, or water desalination and refining. So most of steam applications that are in this field can be nowadays targeted with this solution. Geographically, we are working, let's say, with some partners, and we are trying to, let's say, approach all the most advanced countries. Of course, we are trying to understand where are the preferable markets, especially in terms of availability of low-cost electricity from the grid, and also need and attention to decarbonize. So in this map, you can see, let's say, a sort of integration of geographical areas with the possible applications like heat electrification, integration with diesel gas boilers, green mining, cogenerations, and other kinds of application. There is a huge market. Here we have just painted, according to our present view, in light green, the large markets in terms of megawatt, and in darker green, the giant markets that can be in gigawatt. By the way, US, Australia, India are just nowadays, some of our colleagues are coming back from the US where where these technologies are finding a lot of interest. So we are happy to have been starting this technology to be here and to discuss with you because there will be a lot of to do in the future.